All right, so the main thing I wanted to show from the video is the experiment, this right here. And so she talked about that in the video, that she was looking to balance the torque, the force that makes this swing around on the string. She wants to balance that with the force that attracts this ball to that ball. So gravity attracts everything to each other, no matter what it is. So there's a force of gravity between this ball and that ball. It's just too small to usually see or experience because friction is stronger and it keeps everything where it is. But hanging on a string like this, it's free to move. You can actually observe the gravitational attraction between these two objects. And so the idea is to have gravity attract this one this way, but there's also a torque in the string that would counteract that attraction. And if you can find the point where this oscillates back and forth, you have found the point where the force of gravity, which pulls this here, is equal and opposite to the torque in the string, which pulls it the other way. And you can measure torque. The equation I was telling you that was really long, we have to know that. This right here, that's how she measured the torque. And so we know how to do that. And so if you can do that, that equals the gravitational force. These two equal each other, you can solve for this constant G. And that's what Henry Cavendish did. He found the constant G, which we use in this equation, which measures the force of gravity. Have you used that equation before? I forgot if we went through there or not. So this equation right here equals the force of gravity. In order to get this equation, Isaac Newton, he knew this was a constant, but he didn't know where it came from. And Henry Cavendish did more experiments to get this constant to a precise value. Yes.
Wait, so was she the first person to discover G?
Oh no, she didn't. She just replicated experiments. So Henry Cavendish in 1798, he did this experiment back then, and he's the first. He did this experiment, and she's just replicating his experiment. So she just is doing the same thing that he did, but she knows what he did, so she's copying what he did. So that's all I wanted you to get from this video, is that. Let me go and turn the lights back on. We'll do a few notes on the board. Okay, so the law of gravity, which Isaac Newton formulated in 1700s, is this. So where F of G is the force of gravity. Capital G, gravitational constant. And then M1, mass of one object. M2, mass of the other object. And then R is the distance between the two centers of the objects. I think so. Wait, no, 7.1 still. Yeah, we're still on 7.1 today. So this applies to any things that have mass. So we're not sure how this works, but somehow gravity attracts any two things that have mass to each other. Now, we only really observe gravity on large objects, the Earth to the sun or the Earth to us. But gravity also applies to anything with matter. It's just that friction usually is stronger than gravity for small objects. And so, you don't see your pencil go towards your book because friction overcomes the force of gravity. But without any friction, you would see your pencil go towards your book. Your book would attract your pencil.
So in that experiment, with small design with whatever, would those be one and then two, or would the larger balls be?
Oh yeah, well you could apply it either way, but in that experiment, what's attracting each other? So you have this bowling ball right here, this over here, then you would have the smaller rod right here. So this bowling ball right here is pulling this ball towards it, right? So that would make this ball right here M2 because that's being pulled. So even though there is an attraction between here and here, which you could also measure, it's not really useful to you. You're not really seeing an acceleration. These are staying in place, right? And so this is what she was focusing on right here, is where the acceleration was happening, where you see a movement happen. But you could apply it to any two things. So you definitely could apply it M1, M2 to these two, but it just wouldn't really help you. In the middle? So it would oscillate back and forth at that point. So now, if you have it exactly in the middle like this, and you have no force, it would just stay there because you'd have balanced forces on either side. So if it's exactly balanced like this, you wouldn't see any movement at all. But any little air current at all would move it so that it would go back and forth between the two objects. So the point of the experiment again was to find this value right here, which go write that out again. So it's a very small number.
How did she make like the torque?
Oh, the torque is just a turning motion, which is just, in this case, it was a string attached to the ceiling, and the twirling of the rod is the torque. So any force that causes a turning or a twirling is torque. So it just naturally does that, right? If you attach a rod to the ceiling, the air currents in the room will make it twirl. If you balance it exactly in the middle, you're going to see it naturally rotate around. Have you ever seen that before? Then it would just stay in place. So you have to give it initial push. Like either the air has to push it or you have to push it to start it. So but usually it's going to just do it on its own just because of the air current. But if there wasn't any air current at all, you'd have to push it for it to start. The units on here, you have newtons times meters squared or cube, sorry, squared over kilograms squared. So this is used to measure the force of gravity, which would be, weight is gravitational force. So that's the primary way that we use this equation. So that's one equation that you should have in your note card. We'll be using that one in this chapter. One more equation that's important is this one. This equation right here gives you the time it takes for a planet to go around the sun. So T is the period of a planet orbiting the sun. So basically we define it as its year. You know, for Earth, it is 1 year, 365 days. Other planets, though, a year for that planet is either shorter or longer than our year. Yes. Oh no, this is just the units of this. Those are the units of the constant. And then 2 and pi are constants. R distance between the planet center and the sun center. And then divided by G, so that's just this right here. And then M of the sun, mass of sun. Yes. Exactly, yes. Yeah, that's G times M. This is essentially Kepler's third law, just reapplied. So those 2 equations you'll be using for homework today. Actually, there's one more before we do homework I want to get to. Do y'all have this down?
Wait, what's G and
Yeah, so this is G times M. So it's this constant right here times the mass of the sun. So that's G times M, where it's this constant times the mass of the sun. That will be given to you in your homework. Like around the board too, if you want to put that down, but your homework will always give that to you if you need it. But that's the mass of the sun. So we have this side down on the left-hand side. Okay, last equation today that we'll go to, and we'll talk about some more detail next chapter section. But for today, just in general, it's this. Lowercase g equals capital G times ME divided by R squared. So you've seen this one before, right? Lowercase g. Did we talk about lowercase g before and what that means? So that's 9.8 for Earth. The acceleration due to gravity. So uppercase g is a constant, that never changes. Lowercase g can change based on the planet that you're on. Uppercase letters are usually reserved for constants. lowercase ones generally are not constants. And so uppercase G is a constant, lowercase g does change.
Is the sub just
Exactly, yes. So ME is massive Earth. And then RE is how far away are you from Earth's core? It can't, if you're on Earth's surface, yes. But if you're, say, in space, you know, or if you're in the clouds, then that'd be where you are in the clouds to Earth's center. So it can change based on where you are in the world. And the world itself is not, you know, a constant elevation. So in certain parts of the world, you're below sea level or you're on a mountaintop, you have a greater or lesser R based on where you are at. So if you're on a mountaintop, G is smaller than if you're on sea level or on the ocean floor. You're closer to Earth's surface, you have a higher G. You're going to weigh more than if you're further away from Earth's surface. So on a mountain, you do weigh a little bit less than you do when you're not on the mountain. This gives you a way to find the acceleration of gravity where you are into Earth's core. So you can see how it changes based on where you are. This also says that if Earth were to shrink for some reason, that you'd have a higher gravity. Or if Earth were to expand, you'd have lower gravity. Keeping the same mass, if you were to change R, you would change the force of gravity. All right, so on your book on page 178, work on 6 through 11 for today. Um, 178. Yeah, I would keep them on your note card. We won't use the last one that often, but it would be good. It still would help you to have those 3 on your note card. Yeah, I'd have them all. Oh, page 178, do 6 through 11. Oh, and be sure that when you use R, it's in meters. Always have it in kilograms for mass and meters for R. Yeah. Talk to Lauren? Yeah, I can see. See, I mean, she should still be there. So see if she can hear you.